All right, we're starting the second PowerPoint for Chapter 16. There's something weird going on with the titles where it doesn't show them properly, but I think everything else is coming in fine, so I'm just going to go with it. But this is part 2 of acids and bases. This section is going to focus mostly on the calculations we have to do. This slide, the title is Equilibrium Constants for Acids. Essentially, acid-base reactions, like when I put an acid in water or a base in water, we consider the fact that any reaction that we do in solution of this type can be a reversible reaction. Okay, so if I put an acid in water, it can dissociate, give a hydrogen to a water molecule, and make an H3O. There is the potential that it can come back and reform the acid that I started with, so it's reversible. Specifically, we say that strong acids tend to, the acid dissociates, and the number of molecules that actually come back together again is either 0 or near 0, so it's pretty much a one-way reaction. Okay. Then when we have a weak acid or a weak base, in that case, it's a true equilibrium where you have the reaction going both ways. Okay. So for strong acids, the dissociation, we usually just use a single arrow, and then with a weak acid or base, that's where we tend to use the double arrow for equilibrium. Okay. Now, how much of the acid ionizes? Is it a high percentage or a low percentage of the acid that actually breaks up and gives H plus ions? We can represent that since it's equilibrium. The H pluses are being formed on the product side. So if we do products over reactants, we get our equilibrium constant. For an acid, we call the equilibrium constant Ka. But that value, the bigger it is, the stronger the acid is. All right, so a strong acid, which we say pretty much all the acid dissociates and goes to the product side. In that case, we say that the Ka value typically will exceed 1,000. So the Ka value will be at least 1,000 or more. Okay, what that means is if I put 1,000 HCl molecules in solution, pretty much all, or about 1,000 to 1 ratio, the 1,000 will break up for every one that stays together. Okay, that's close enough to complete ionization that we usually just say it's a one-way reaction. All right, for let's say acetic acid, which is a weak acid, its Ka value is 1.8 times 10 to the minus 5. That's a very small number, which tells me that only a very small fraction of the molecules, when I put acetic acid in water, only a small percentage of them are actually going to dissociate. And I think with acetic acid, it's usually on the order of like 1 to 5% that ionize. Okay, so the value of Ka can give us an indication of how strong an acid is or how weak it is. So strong acids, Ka is greater than 1,000. Weak acid tends to be less than 1. Usually it's a lot less than 1. There aren't many acids that are in that middle range. It's either a really big Ka or a really small Ka. We can find these values when we start doing calculations especially with weak acids and weak bases. We can find the equilibrium constants that we need in the appendices. Specifically, it's Appendix D of your textbook. Or you can find Ka values online. Just be aware when you look for Ka values online, sometimes the numbers that are reported in different textbooks will be different from each other. Okay? These are measured values. Sometimes the conditions or how the numbers are measured can vary from book to book. So if you're doing Master in Chemistry or working the worksheets and want to get the answers that we have, typically you want to use the numbers from our book for consistency. And then the formula for a Ka reaction, there's actually 2 ways it can be written. If you include water in the reaction, we say Ha reacts with water, or when you put it in water, when the acid gives a hydrogen away, the hydrogen goes on the water molecule, makes an H3O, and then what's left of the acid, the anion becomes A minus. Okay, so this would be the representation of a weak acid. Remember I said a weak acid, I'll show the double arrow that represents equilibrium. If it was a strong acid, I would tend to just put a single arrow to the right. Okay. Now I can also write this reaction. If I leave water out, I'll just say HA yields H plus A minus. Okay? Remember, H plus and H3O plus are basically the same thing. It just depends on whether you show that water molecule or not. So honestly, it's less writing to just say HA yields H plus A minus. There's less to write there, and on the test, I want to be fast. I want to get my ice table set up on a problem that needs an ice table. So I prefer the shortened form of this reaction over the one that's on the slide. And then once you write your reaction, my equilibrium expression, Ka, which is the equilibrium constant for an acid dissociation, Ka, equals the products go on top, the reactants go on the bottom, but water is a liquid, so it does not appear in my bottom of my equation. It gets lumped in with the Ka value. All right, so that's the expression I come up with. And anytime I'm doing a weak acid calculation, I'm going to use a reaction like that, and I'm going to use the Ka equation like this. This is the standard formula for what they look like. It doesn't matter what the acid is. Honestly, anytime I'm doing a monoprotic weak acid, monoprotic means an acid that only gives up one hydrogen, the reaction's going to look just like that, and then when I set up the expression, it's going to look just like this. Okay? So you definitely want to just memorize that. All right, so some examples of your Ka values. Again, this is from a different book. The numbers are here, but obviously you probably can't read it in the slide. But I look in here, and if I'm doing a problem that involves acetic acid, I just have to find the place where acetic acid is listed, and acetic acid's right here. There's the formula. The Ka is 1.8 times 10 to the minus 5. Okay? I find the number I need, and then I work through the problem. So, if I want to calculate the pH of a solution that is 0.1 molar HCl, I said in the first PowerPoint, when we have a strong acid, and you're supposed to remember that HCl is a strong acid, the concentration of the acid equals the concentration of the H3O plus ions. Okay, now, why is that? Let's talk about it. Let's show it in the form of an ice table. So there's my reaction. HCl will dissociate to form H plus and Cl minus. That's how I'd write the reaction if I'm going to leave water out of it. Technically, the H plus is really going to be an H3O plus, but it's close enough that it'll work. Okay, so when I set up my ice table, ICE, I got my initial numbers. The 0.1 molar HCl goes there. The amount of H plus and Cl minus before the reaction is essentially 0. Now, I will say, let's be careful that in reality, if I'm doing this in water, let's keep in mind that the H plus concentration, technically there is a tiny little bit in the solution from just the auto-ionization of water. If you remember, the H3O concentration in water is 1 times 10 to the minus 7 molar. That's a tiny number, so it's probably going to be insignificant, meaning the amount of H plus that I make from this reaction is going to be a much larger number than what I already had. So normally, even though it is an assumption, but I assume that this number is 0, even though in reality, it's not. It's a tiny, tiny number. Okay? We will explore at some point an example where that assumption might get us in trouble. So, with a strong acid, all of the HCl is going to dissociate. So I know that I start with 0.1 molar initial. The change, if all of it dissociates, I'm going to subtract the whole amount, which leaves me with 0. The HCl in solution, if it all dissociates, there's no HCl remaining once it reaches equilibrium. Okay? Well, it's a 1-to-1-to-1 reaction, so if I'm using 0.1 here, that means I'm going to gain 0.1 here under H plus and 0.1 under Cl minus. So my final amount, I have 0.1 molar H plus, 0.1 molar Cl minus. Well, if I'm calculating the pH, the important value there is the equilibrium H plus concentration. Because that's the one for the pH. It's going to be the negative log of this number. Okay, so if I do that, you should get a pH of 1.00. Now again, if you remember sig fig wise, the concentration that was given had 2 sig figs. So my pH that I write should have 2 decimal places. The decimal places of the pH should match up with the sig figs of the concentration. Now, what about a weak acid? So I have 0.1 molar acetic acid. There's my reaction. Now, again, formatting, it should be a double arrow right here for equilibrium. It's just the computer always loses that. But that acetic acid reacts with water to form acetate and H3O+. Again, I can set up an ice table. Notice this time I'm showing the water molecule, but in a ice table and in my equilibrium expression, this is a liquid. So pretty much I can just ignore it all the way down. It doesn't play a part in my ice table, or at least those numbers aren't going to be important, because when I go to the equilibrium expression, I'm going to leave them out anyway, because water won't be part of the equilibrium expression. All right, so I got my initial amount of the acids 0.1. Again, the amount of these is going to initially be 0. But this time, I know that the acid is going to dissociate partially. Some of the molecules will break up. I'm going to make some H+ ions, but the problem is I don't really know how many. So I'm going to have to plug in an X, meaning X is going to be less than 0.1, but greater than 0. I'm going to have to solve for that value. How much it breaks up? Well, all I do know is that the number that break up here is a 1 to 1 to 1 reaction. So I'm going to lose X here, but I'm going to gain X here and here. So then I can break down my values. I get 0.1 minus X for the acid. I get X for the acetate and X for the H3O+. I can take those numbers, set up my equilibrium expression. Acetate times H3O+ over acetic acid equals Ka. Now to solve this problem, again, if they want me to find the pH, that's going to come from this number. So I'm going to be solving for H+ concentration. Oh, excuse me, actually this one, but it's the same thing. I got to solve for the H+ concentration, which means I can only have one unknown. If I'm solving for this value, that means I need to know what Ka is. The problem didn't give it to me, but you're supposed to know that if you need a Ka value, you have to go to the appendix, find the value you need, and then plug it in. So, the Ka value for acetic acid is 1.8 times 10 to the minus 5. So I plug that in right here. On top, I have X times X there. On the bottom, I have 0.1 minus X. Now, the top, X times X, is going to be X squared. The bottom, we've actually simplified. Like if I solve this equation as it is, X squared over 0.1 minus X, the only way I could solve for X there would be to do a quadratic equation. Okay? I don't want to do a quadratic equation unless I have to. There are times that you have to do it, but there are also times where we can avoid it. This is one of those times where we can avoid doing the quadratic by doing a mathematical simplification. All right? So what we're going to do is we're going to look at the bottom and say, okay, the acid concentration is 0.1 molar, and then I know that acetic acid is a weak acid. Its Ka value is 1.8 times 10 to the minus 5. It's a very small Ka value. So what that tells me is the amount of products I'm going to form is going to be a tiny number. If Ka is small, it means I'm going to form a small amount of products. Okay? Now, think about if I go shopping and I have $1,000 in my pocket and I buy a pack of gum. How much money do I still have? Okay? Now, some people might get really technical and say, oh, you have $999.75 if it was a cheap pack of gum, right? So you can get technical and find the exact value, but really, a lot of people would say, well, if you have $1,000 and you buy a pack of gum, you essentially still have pretty close to $1,000. The amount of money that I spent is fairly insignificant compared to the amount of money I have. Okay? That's what we're looking at here. The 0.1 minus X, the 0.1 concentration in a solution is a relatively high value. The minus X is like the cost of a pack of gum. Only a tiny amount of the acid is actually going to dissociate. So the amount of the acid I still have in solution is going to be pretty close to the original number, 0.1. I'm not going to lose very much of my acid. Now, what that does for me, if I can make that assumption that the amount of acid that dissociates is insignificant, that lets me drop the minus x from this expression right here. And then that simplifies my equation. Instead of x squared over 0.1 minus x, if I can drop the minus x, then it becomes x squared over 0.1. That's a much simpler expression to solve if I get rid of that minus x. Instead of having to do the quadratic, if I'm just looking at this, all I have to do is multiply 0.1 over times Ka and then take the square root. If I do that, I'm going to find that my value of x, which is my H plus concentration, is 1.34 times 10 to the minus 3 molar. And then if I do the negative log of that, I'll find that the pH of the solution is 2.87. Now, if I make that assumption, it changes my answer a little bit. The true value, like if I make the assumption and solve for x, or if I go with the original equation and solve for x doing the quadratic, the one with the quadratic is the correct answer. The one where we made the assumption is close to the correct answer, but it's not exactly correct. So then we have to think about, okay, when can we do it and when can we not? Like, how do I know if the assumption is going to change the answer too much? Okay, so we have a rule of thumb that we apply. The rule of thumb is that we're going to compare the value of Ka, of the acid, and the initial concentration. If the initial concentration is at least 1,000 times bigger than Ka, then we're allowed to make the assumption. If it's at least 1,000 times bigger. So if I divide 0.1 by 1.8 times 10 to the minus 5, I think if you do that, you find that it's like 5,555, I think is the number you come up with. So initial concentration divided by Ka, if that ratio is at least 1,000, then you can make the assumption. If it's not 1,000, if it's less than that, then you need to do the quadratic. Okay? Because the closer they are to each other, the more significant that assumption becomes. And it can actually mess your answer up. Okay? So, that's our rule. So let's look at another example. So now I have another acid. It's not one that we're familiar with. It's just a random acid called chlorobenzoic acid. I know that I put in 0.1 molar solution. That's the concentration. I measure the pH with a pH meter, and it reads 2.50. We want to solve for the Ka value. So again, when I look at the reaction, HA plus water yields A minus plus H3O plus. Even if you don't know the formula of the acid and the conjugate, you can write that general equation, and it's a lot quicker. You could even just say HA yields H plus plus A minus. For any general acid, you could use that equation instead of writing out the whole equation that's up on the board. Okay? So simplify where you can. It'll save you a little bit of time. But then my ice table, again, my initial concentration is 0.100. Now this time, they gave me the pH. The pH of the solution was 2.5, and from the pH I can find the H plus concentration. The pH equals the negative log of the H plus. Well, if I move the negative over and then do the anti-log, which is on your calculator, that's the 10 to the X button. So if you do 10 to the negative pH, that gives you the H plus. It's just rearranging that equation. Okay, so 10 to the negative pH gives me that. That's the H plus concentration that I need to put in my ice table. Again, the pH is going to be, it's the H plus at equilibrium. It's negative log of the H plus at equilibrium. So I'm going to plug that number on the equilibrium row. That number goes in the H, actually it should be in the H plus spot. So I put it in the wrong place. It should be right here under H plus. But either way, these two are the same because it's a one-to-one reaction. All right? So now from that, I can actually fill in the rest of the table because if it's 0 plus x gives that, that means that this number has to be x. And that means it's x in all three rows. So this number goes here, and here, and here, which allows me to fill out all the numbers. So once I have all the numbers on the equilibrium row, then I can do products over reactants. In my expression, products over reactants, I can plug the numbers in. So I get 3.16 times 10 to the minus 3 squared over 0.1 minus 3.16 times 10 to the minus 3. Solve that. We get that our Ka value is 1.03 times 10 to the minus 4. All right, one more problem on this slide. We have lactic acid. Again, it's just another random acid, so you could write HA yields H plus A minus for your reaction. We want to calculate the initial concentration of the solution, so the initial acid concentration. If the pH is 2.5 and the Ka is 1.4 times 10 to the minus 4. Again, we have a reaction, but I would write the simplified one if it were me. When I fill in my table, this time, again, I can use the pH to find the H plus. That goes under this one right here. Again, that tells me what the X's are, so I know everything in the table, except for this time I want to know the initial concentration of the acid. So I'm solving for C right here, but C minus X ends up giving me this. So now once I set all that up, and again, you need to do that yourself, then I can take my equilibrium row, plug it into the equilibrium expression, A minus times H plus over HA, plug in all my numbers from up here. There's my unknown, is my C value. Then I just have to do some algebra to solve for C. You should get 7.45 times 10 to the minus 2 as my answer. All right, that's a good place to cut off. We'll keep working problems in the next video.